Hello everyone, and welcome back to the series of lecture on actinides chemistry. In the last lecture, we have studied about some spectroscopic aspects of lanthanides and actinides, and in continuation to that, we'll try to understand some of the utilities of the emission spectroscopy. And here, as we have also discussed in the last lecture, that how we can record this spectra, that is the excitation spectra, emission spectra, and lifetime spectra. And here the excitation source we are using is basically some electromagnetic wave, that is basically UVVs generally we use. We generally say it is like photoluminescence, and in short form we also say it like PL studies. So in this photoluminescence we excite with the source and then we measure the emission, and we'll try to extract some of the information that we are getting from this excitation spectra and emission spectra, as well as on the lifetime spectra. So in brief, I have told you that how to measure this excitation spectra. In the excitation spectra, or to measure the excitation spectra, first thing you have to do, you have to fix the emission wavelength. You have to fix it, and once you fix it, then you just scan the excitation monochromator, and then you'll be getting some peak. So suppose I'm taking an example of europium 3, then this peak generally comes around 394 nanometer. So this is my excitation in which my emission is fixed. So my emission is fixed. When I talk about the emission spectra, what I'll do in emission spectra, since I know this is the peak, that is the giving the maximum excitation, I'll fix my excitation at this peak, and then I record the emission spectra. So by that we are having information about the excitation spectra, we are having information about the emission spectra. Then what we will do, we'll take this maxima and this maxima, we'll fix these two maxima, and we'll try to record the decay half-life, or the half-life of the, or the decay life of the complex that we are interested in. So as I showed you that we can measure excitation spectra, we can measure emission spectra, we can also measure the emission half-lives. We'll talk about that emission half-life later. So what are the information that we can get from this excitation spectra? I've shown you several excitation spectra that I've taken from Google. So you can see there is a difference when you start from A to E. You can say sometime you are getting, most of the time you are getting peak in this region, and that is the excitation spectra of europium with some complex. So you are getting a peak at 394. But if you see, there is a difference here, and sometimes you get a peak here. So what this suggests, and what kind of information we can draw from this kind of spectra? Let us assume that you are having a two complex, then one complex I say is europium L, and the other complex you can say is like europium L2, let us say this is L1. And I'm just arbitrarily assigning europium L1 to this spectra and L2 to this spectra. So just by looking at this spectra, what I can say, there is a difference in this region. What it says that these sharp transitions are in both the spectra. So we know that the FF transitions are sharp, but you can see this transition is not sharp. This is a broad transition, and it is not an FF transition. Rather, it is a charge transfer band or charge transfer transition. So what we can say from this charge transfer transition or charge transfer band is that out of these two complex that I have written, to say L1, L2, this particular ligand, that is L2, having a better overlap or more overlap to europium rather than L1. So what it is doing, there is a charge transfer. You are exciting the ligand, and ligand is transferring its charge to the europium, and from there you are getting some emission. So we can get this kind of information from the X-ray spectra. Even in certain complexes, the charge transfer band is so large, or you can say so intense. Suppose you take the spectra of europium with TTA. I hope you must have heard this name TTA in your extraction classes. If you take the spectra of this, the charge transfer band is so huge, you can say that these transitions are just like very small as compared to the charge transfer band. So the information of the metal ligand or overlap can be seen from this kind of spectra. Okay, now you have some excitation spectra, and then you are sitting on the excitation maxima, let us say here or here, whatever excitation maxima you choose, and then you record an emission spectra. So suppose I sit on some maxima, and then I record the spectra, and suppose again I'm just arbitrarily assigning it L1 and L2, and you get some kind of spectra like this, europium L1 and L2. So what, just by seeing this spectra, one thing is very clear to me: the spectra do not look very much similar. So what I can say that the environment around europium in the two complexes are different. What it is, we'll see later, but it is different. Obviously, this is different from this. So this is the direct information that we can get from emission spectra. But if we look it very closely, then we can see there are several transitions that I have marked here. And you know that we start with FD0, 5FD0, 5D0, and we give transition to 7F0, 7F1, 7F2, and all these transitions are marked here. So let us say the first transition, that is 5D0 to 7F0. Many times we just say this is J0 and this is J0. So many times we just say it is like 0-0 transition. Sometimes I'm also using the term like 0-0 transition. So if you see this 0-0 transition, then it is like 0-1, this is 0-2, like that. You can name like that also. So the information that is there in the 0-0 transition, let us see. So your 0-0 transition, but this is my 0-0 transition, that happened to be found near 550 nanometer for europium. We also know that the transitions that we say that are coming from 5D0 to 7F0 to 7F1, we have seen that there is a splitting of J level. There is a splitting of J level, and this J level will split into 2J plus 1 states that I have seen in the previous slides, I guess. Yeah, you can see that this J level, depending on the symmetry, can split maximum into 2J plus 1. So, but when we say about the 0-0 transition, what is the J value? J is 0. So your 2J plus 1 will 1. So you can say even in symmetries of different environment, this transition cannot split. What is the use of this? Let us say I have a spectra. I have just recorded a spectra. I'm getting a peak like this, and the reason that is maybe 577 to 579 or so, I'm getting these two peaks. One thing I'm sure, this is not the splitting. Why? Because it is a 0-0 transition. So what information it gives to me, that there is at least presence of two europium species, with two different luminescent species of europium are present in the complex. So this kind of information I can directly get from this 0-0 peak. Let us say the other peak, that is 0-1 peak. The 0-1 peak can split into J plus 1, giving rise to 3. So if you are having this peak, as you can say in this spectra, there is some splitting. Similarly, when you are having to 0-2, this can give you 5 peaks. So it can split into maximum of 5. This all depends on the symmetry around the europium ion. So lower is the symmetry, more is the splitting. So we can get information about the symmetry class if you know splitting of all the lines, and then you have to just see the table, and suppose you are having some system which is having hexagonal symmetry, and if you just see, the first should be 1, then the second should be split into 2, third should be 3. Likewise, if you see, if you are matching with splitting of the pattern is matching with this table, then you can safely say that the symmetry around my europium ion in this particular complex is hexagonal. So you can get that information also from this. There is one more thing that we can known as asymmetry ratio. So suppose they are having a transition 0, 1 and then 0, 2. And we are having two transitions. 0, 1 transition we have discussed, it is called magnetic dipole, whereas 0, 2 transition is called electric dipole. We have also seen that this magnetic dipole transitions do not get much affected by the ligand environment. So if we take the ratio of the electric dipole transition to the magnetic dipole transition, we are getting something that is called asymmetry ratio. That is, we are taking a ratio of the electric dipole transition with the magnetic dipole transition. What it means that the 0, 2 transition divided by 0, 1 transition. And in a typical spectrum of water, if you take this ratio, the water spectrum is like this one, then this. So this is your 0, 1, this is your 0, 2. And if you take the ratio, it will be somewhere between 0.5 to 6. So generally it so happens that when there is increase in this ratio, we say that the asymmetry around the europium ion is increasing. So that asymmetry information also sometimes we can derive just by using this asymmetry ratio. So now we can derive some information. Okay, we know this is the symmetry and this is the kind of complex that is there with the europium. Now let us try to see how we can deal about the lifetimes. I'll come back to this slide after some time. Yeah. So we also can record the lifetime in which we fix the excitation spectra, we fix the excitation wavelength, we fix the emission wavelength, we fix both at certain wavelength, and then we give an excitation pulse, and then we monitor the decay. And when we are getting this kind of decay, we simply use this equation to fit this decay. And depending on the nature of the complex, we can get different lifetime. But generally we start with a mono-exponential fit, and then suppose we are not able to fit it, then we go for the bi-exponential and tri-exponential. But generally we restrict ourselves to bi-exponential only, but can fit it into different kind of exponential until once you are getting a good fit, but not more than bi or tri, because if you are using a very high exponential, then it gives a good fit, but it is logically not very valid. So why the lifetime is getting decreased? Generally assume that for the lanthanide cases or the actinide cases, the decrease in lifetime is mainly due to the water. We can say it is the OH vibrations of the water molecule. So most of the time we assume that the decay in the lifetime is mainly concerned with the vibration of the OH oscillator of the water. If water is the only responsible ion for the molecule for the decay, then we can directly relate the number of water molecule in the primary sphere to this decay curve, and it has been done. And this is the relation, this is the linear relation basically that directly relates the number of water in the primary hydrogen sphere to the decay lifetime. So you have to just fit the curve, you will get the decay constant, and from the decay constant you are just putting into this equation, and from this equation you can getting the number of water in the primary hydrogen sphere. And for europium, it so happens that the lifetime in water is coming around 110 microsecond, which is giving you the water molecule around 8 to 9. So for europium, we can get this 8 to 9 water molecule with a lifetime of around 110 microsecond. Okay, what is the utility of this? Let us assume that you are having europium with let us say 8 water molecules. 1, 2, 3, 4, 5, 6, 7, 8. And then you add a ligand in the system. And suppose your ligand is a bidentate system. What will happen? We assume that it will just go and bind to the metal ion. So that now my ligand is here. So you can say out of the 8 positions, 2 positions are occupied by the ligand molecule. Now if I just measure the lifetime of this molecule, and we'll get the number of water molecule, which we are getting 8 in the case of europium with the aqua ions, or in the aqua hydrogen sphere. This should be reduced to 6. So if the hydrogen number is reduced to 6, we can say yes, there is some complex formation. Similarly, suppose you increase the ligand concentration or the pH depending on the nature of the ligand, you may be getting 1:2 complex. And assuming again a bidentate ligand, then 4 water molecules should be replaced, and then by fitting this equation you should be able to get 4 water molecules only. So that to exemplify that, I've given you the example of composition with some polyamino carboxylate. And this is for curium, and they again for the curium you can see this is the equation they use. These are the various different polyamino carboxylate ligand. And if you see the first one here, you can see you start here, which is the hydrogen number of around 9 to 10, and the moment you add this ligand at pH 2, there is sharp difference in the number of hydrogen pair. What does it mean? That at this pH there is a strong complexation. That now your ligand is complex and most of your water molecule has been removed. Compared to that, if you see this curve, there the number of primary hydrogen pair are still intact. There are some water molecules in the primary hydrogen pair. So you can say about the denticity of the ligand, that will affect by the denticity of the ligand. Here you can maybe having a 1:1 complex, or here maybe you are having 1:2 complex. But whether it is 1:1 or 1:2, we cannot say directly by this, because that will depend on the denticity. Suppose you are having a ligand which is having such as EDTA. Even with 1:1, it can remove mostly all of the water molecule from your inner sphere of the metal ion. This is for NTMide again. You can see the two plateau. At certain pH, you are having 1:1. If you increase the pH, you are getting 1:2. So just by recording the lifetime at different pH, you can have some information about the number of water in the primary hydrogen sphere, and you can also tell something about whether it is a 1:1 complex or 1:2 complex. Till now it is okay. Let us say we are having only one species, the things are looking very easy till now. But suppose in the system we are having more than one species. Suppose you are having, let us say, 2 species. You are 1:1 and few are 1:2. You are having a mixture. In those cases, what will happen? That instead of a mono exponential curve, you will get some curve which can easily be fitted into a bi-exponential curve. You'll get a curve like this, and when you fit it into the mono exponential, you may not be getting very good fitting. Then you go for the bi-exponential fitting, and you are getting some good fitting. So now you know that your system is having more than one species based on the lifetime spectra. But suppose I want to know that what is the emission or excitation spectra. Remember that this excitation and emission spectra that we have recorded in the steady state. When I say steady state, it means there is nothing to do with the time. We have just excited and we have recorded. But the decay lifetime says there are 2 species, and suppose I'm interested in getting the spectra of both the species. That okay, what is the spectra of the short-lived or 1:1 complex, and what is the spectra of the long-lived or 1:2 complex. So now, as I was telling about that, suppose you are having 2 species, and you want to know that what is the contribution, or rather what is the nature of the spectra of 1:1 and 1:2. For those kind of cases, we cannot use the steady state emission profile. Why? Because there is no timing information. But from the timing information, that is the lifetime spectroscopy, we know that one species is decaying faster than the other. For simplicity, I have assumed 2 species. Let us say you have a system which is having 2 species. One is decaying with the lifetime of 100 microsecond and another with a 500 microsecond. When I say lifetime, I mean this value is 100 microsecond. When we record the spectra, if you look it carefully, suppose you record a spectra which is given like this. The species with 100 microsecond will decay first. and the species with 500 microsecond will be having a long tail. Why? Because the decay constant that we derived is just by fitting this equation. If you see this equation, these two equation, then we can say, okay, 100 is decaying very fast compared to the 500, which is obviously giving you a tail, and I want to record the spectra. So initially with a steady state, suppose I record a spectra which looks like this that I've given here, and this is a steady state, that's I have written t equal to 0, and for simplicity I assume that these two peaks, this peak and this shoulder, is coming from the shorter component, that is 100 microsecond component, and the rest of the spectra is from the 500 microsecond component. So what I want to record both. I cannot do with the steady state. So now what I will do time resolved fluorescence spectroscopy. In this, what I will do, I will excite my complex with the wavelength, that is say 394 in this case, and then I'll wait for certain amount of time. Why to wait? Because suppose I excite at this particular time and I'm waiting for this time. This is my waiting time. This is time I'm waiting for, and then I'm recording spectra. What will happen? Let us say you have 100 and 500 and you are waiting for around 500 microseconds. So suppose this limit is around 500 microseconds. If we see the decay of the 100 microsecond species in the 500 microsecond species, you'll find that if I am waiting up to 500 microsecond, you have given almost 5 life to the 100 microsecond species. Whereas for the 500 microsecond, you have given only 1. Right? So if you see the decrease, if you see that the intensity, which is a combination of both 500 and 100, but if you see the decrease is this. The intensity decrease is proportional to e to the power t by tau. And in this case is my t is my waiting time. So my t is 500 and my tau is only 100. So here I'm getting a value of 5 e to the power 5. So you can see my intensity at around 500 microsecond is nothing but I naught divided by e to the power 5, which means that there is a decrease of almost 140 times. So there is a decrease of around 148 times in the excitation state of the smaller component, whereas if you see the longer component, it has only one half life or one decay life. So for this, the decrease is just like 2.72 times, or mainly the signal that is there is 63% from the L2 and hardly 1% from the L1, or you can see the shorter component. So if you are giving a decay and you are measuring after a decay, the profile which you will get is mainly composed of the long lived component. So I am expecting that this peak should be not there, the first peak, then we are getting second peak, and the shoulder should not be there, and we should get a peak. So if it is a spectra of A plus B, then this should be the spectra of the B, assuming that B is having a lifetime of 500 microsecond. So in this way, you know A plus B, you know B, and you can subtract A plus B minus B. It is not that direct. You have to understand the quantum fields also, but assuming that everything is similar for both the complexes, I can say that you can just subtract it to get the A. So you can record the excitation spectra as well as emission spectra using this time resolved fluorescence spectroscopy. So now we have some idea and some application of this spectroscopy. Now I just want to have a very brief discussion about the redox property that we have already discussed, but I just want to give you some of the examples that for the actinides. I have already discussed to you about this table, that what are the redox potential of different actinides, and from this table you can easily see that some of the redox potentials are way on higher side. So let us say for thorium it is high, so it is very difficult to reduce thorium 4 to thorium 3. But some of the actinides such as plutonium having redox of around 1 volt, so there are a lot of chemistry, a lot of redox chemistry can happen. So why we need require this redox chemistry? Because many times it happens that we require this for the separation, because most of the time our separation is based on the oxidation state of the metal ion. And you must have heard and you must have listened this Purex process. About the Purex process, many a time we play with the oxidation state for their determination. That is the generally we do for the uranium estimation using a Davis-Gray method. And suppose you want to understand the chemistry of the refined oxidation state, even in those cases we want to have information about the redox potential, so that we can play with the redox potential and with certain complexing agent, or we can add some some different kind of redox couple that can either easily reduce or oxidize metal ion. So to exemplify, suppose I have given a very simple example. Let us say that from our classbook chemistry, suppose you are here having a couple of iron that is getting reduced to iron 2, and you are having a couple that is between iodide and iodine gas. So suppose I take these two and I'll mix them, and after that I'll just add a drop of starch. What I found that the color of the solution is becoming blue. Why the color of solution is becoming blue? Because if you see this couple, it so happens that the reduction potential of this is 0.77, the first one iron, and the reduction potential of this is low, let us say 0.54. So it so happens that iron will get reduced, whereas this will go oxidized to iodine gas, and when you are adding starch to the iodine gas, it will make a complex that will be blue in color. Now to this blue color you add few drops of EDTA. Now what EDTA will do? EDTA can complex iron 3 plus and iron 2 plus. And the moment it will complex, their redox behavior will change. Now the reduction couple is no more 0.77, rather it decreases to something like 0.12. And since the redox potential has been changed, so the course of reaction will change and you will get a colorless solution. Why? Because now there is no more iodine. Now what you are getting is, now iodine is getting reduced to iodide and your iron is getting oxidized to iron 3 plus. So this is the variation in the redox couple I just want to emphasize, just by addition of some ligand. How we can do it mathematically? It is a very simple equation that I have taken from a paper. You can just easily see that. Suppose we are having a redox couple, that is M plus is going to Mn minus 1, and you can always write delta G for that. Similarly, suppose there is a complexation. For the complexation, you can again write. So this is the we have started with the oxidized one. This is the product, the reduced one. Again, you can write for the complexation. I am assuming that L is a neutral ligand. And when you write this, you can write the corresponding stability constants also. That is Km and Kmn. And with simple mathematical juggling, what you found that you can easily write this equation. And if you closely look at this equation, then now you are not talking about the pure metal ions. Now you are talking about the complexes. The Ml complex is getting reduced to MlQ complex with the total gain of n electrons. So now we are talking about the redox potential of this particular couple. And if you see mathematically, what we found, if you drive the equation for this, you found that the E naught complex is nothing but E naught aqua minus RT upon NF ln Km upon Kmn. This is the important term. Why? Because now your potential is totally dependent on the stability of these two complexes. As I've shown you that EDT example, that the complexes of EDT with iron 3 and iron 2, their stability must be different. So their stability constant must be different. So which is more stable, depending on that, you will get a potential which is either left shifted or right shifted. Your potential may be more negative than the original one, or maybe more positive than the original one. Generally, it so happens that when you are adding some kind of complexing agent, some of the complexes get stabilized and you will get a reduction at the lower potential. And this is again, just I have shown you that the Davis-Gray method. It is a very important method in the estimation of uranium in the nuclear industries. Here what people have done, that they played cleverly with the redox potential of iron complex, iron couple and uranium couple. So if you see that the iron couple having a potential of around 680 millivolt in sulfuric acid, but the moment you start adding phosphoric acid, there is a decrease in the reduction potential. Whereas under similar condition, if you see the couple of uranium, it is almost unchanged and then rising. So here if you see that the reduction couple of iron is higher side than the uranium, whereas the reverse is true here. What it means that here iron will try to reduce and uranium will get oxidized, whereas here uranium will get reduced. So now you are having uranium 6 that will get reduced to uranium 4. So now uranium 6 will get to uranium 4. Uranium will get reduced and iron will get oxidized. So just by changing the media, we can see there is a huge effect of medium on the potentials. And just by playing the media, we can play with the redox potential, and that is generally used to carry out different transformation, that redox transformation, even for the actinides. But instead of metallic reducing or oxidizing agent, we are mainly preferring something which is kind of more organic. So hydroxylamine hydrochloride or hydrazine or sometime hydrogen peroxide, they are mostly used in changing this couple of actinide, and some of the reagents that are generally used for neptunium in aqueous phase are given here, and similarly for plutonium also I have given here. So this is just to make you understand that in different kind of media, the potential can shift here and there, and this understanding of potential and this understanding of their shifting with different kind of reagents are generally used for their either selective reduction or selective oxidation. And these processes, along with the extractant that we use, are generally used for the separation chemistry or understanding the chemistry of lanthanides and actinides into the aqueous phase. And with this, I just want to end today's lecture, and thank you very much.